Okay, the today's lecture would be very important. Okay, last time you were here, right? So let me refresh your memory. From programmer's point of view, right? Programmer's point of view, you have a register file and main memory. Only register file is visible to you. Okay, you cannot see the caches. Okay, so your program, right? Your program is located in main memory. What is your program? Simple, right? Code and data. Code and data. Now you want to process that data with your code. And what is code? Code is composed of what? Composed of instructions. CPU is providing, right? CPU is providing its own instructions. ARM is providing its own instruction. x86, Intel, its own instruction. RISC-V, its own instruction, right? So code is simply collection of instructions, many different instructions, addition instruction, subtraction instruction, memory access branch, and so on. With those instructions, you want to process data, and those two, code and data, those are located here. Okay, and you need very small, you need very small but super fast memory component inside CPU, because you need to place data from main memory to register file for processing, okay, for addition operation, for example. Okay, so that is big picture. Okay, so now we will talk about what? We will talk about instructions, right? ARM instructions. Okay, ARM instructions. This one, Hyungjin, can you please? Hyungjin? Okay, Seokhi? Yes, I can hear you.
Okay.
Okay.
CPU provides many instructions. It would be time-consuming to study all the instructions CPU provides. There are essential and common instructions. Instruction categories: data processing instructions, arithmetic and logical integer.
Okay.
Memory access instructions, load and store, branch instructions.
Okay, thanks. So let me show you is all the instructions ARM is providing. You can click on this. This one, ARM version 7, AR, right? Application and real-time application processor. There are 3 flavors of ARM Cortex processors, right? A, application processors. R, real-time processor. If you click on this, ESCA, okay. Chapter A8, you can check out A8.8, A8.8. That is listing all the instructions in alphabetical order. Taking time, huge document, right? 2,700 pages. Please. Okay, so here, A8 instruction descriptions, right? ARM is providing, and here, alphabetical list of instructions. Look at this. From ADC, right? From this instruction, probably addition with carry, right? Addition with carry, then scroll it down. So branch instructions, some instructions I don't know. Okay, some compare instructions. So, and logical instruction, exclusive OR instructions. Some instructions for hypervisor, virtualization, right? So you are using virtual machine, right? Virtual machine to run different operating system, Windows and Linux, on the same physical, notebook computer, right? For that, you need those instructions, hypervisor instructions. So if you, look at these instructions, there are hundreds. There are a lot of instructions, right? And the point is, you don't want to study, each and every instruction before you write program, right? Because so many instructions, right? So I can give you some tip. Then what kind of instruction you need to study? So those instructions, essential and some common instructions, essential instructions. And the question is, what are essential instructions? Those instructions. Data processing, memory access, branch instructions. If you recall my architecture class, I explained to you, why those three are essential instructions, right? So think about those instructions with this very simple, oversimplified hardware block diagram, computer block diagram. That is CPU, and you have memory. Here, code, right? Your program is composed of two, data. That is your program, right? And code is simply collection of instructions, addition, memory access instruction, and branch instruction, and so on. And you have some data you want to process, right? I don't know, right? So you want to add these two, for example, add these two with that code, and then place the result into here, probably. 1 plus 2, 3. You want to place it here, 3 plus 4, and 7. Assume that is the purpose. Okay. So input data, and you want to store addition outcome here with this code, right? That is an assumption, right? Then think about that. So the main reason you want to use computer is what? The main reason you want to use the computer is you want to ask CPU to do some arithmetic operation, addition operation, subtraction operation, multiplication, division, and so on. Because that guy is so fast, so good at processing those data, right? It is able to, if that is running at 1 gigahertz, that means what? Okay, you have to think about the meaning of this clock frequency. What does that mean? In 1 second, right? 1 second, there are 1 gig, right? Billion, 10 to the power of 9, 1 billion pulses, right? 1 billion. So first pulse, second pulse, 1 billion. In Korean, 10억, right? Pulses within 1 second. And computer can do 1 arithmetic operation in 1 clock cycle. That means 1 gigahertz operating frequency, computer can do 10억, 1 billion additions per second, every second. So fast, right? So that is the reason why we want to use computer. You want to ask computer, CPU, to do some operation, arithmetic operation, right? So that is why you need those instructions, arithmetic and logical instruction. Okay, so you want to ask, okay, ALU, please do addition operation for me. Okay, but okay, so I justified the first instruction, why you need first instruction. How about second category of instructions, memory access? The problem, okay, so you want to ask computer to do the data processing operation, addition operation, subtraction. But the problem is when you turn on the computer, if you turn on computer, CPU does not have anything, absolutely nothing inside the CPU. There's no data inside the CPU. No data. Data is present in here, memory, right? So before processing data, you have to place 1 to here, 2 to here, Okay, then you can ask CPU to do addition operation. So that is what? That is memory read operation. Memory read operation. Okay, you are reading one and place into some register. For example, R2, I don't know, 2. Okay, I want to place it to R3 register. Okay, with memory read instruction. In ARM, we have LDR instruction, load instruction. Load, right? You are loading data to register file. And after arithmetic operation, 1 and 2, okay, you do arithmetic operation, output is stored in R4 register, for example. Okay, then after computation, you want to store that into memory because you have only limited 16, limited number of registers, very small number of registers. You have to make room. You have to free this register to load another, data, other data. Okay, so for that purpose, you need memory write operation, memory write, store operation, read operation, write operation, load operation. In other words, load operation and store operation. In ARM, we have STR instruction, LDR instruction, store instruction, STR. Okay, so you need, I justified second category of instructions. You need memory access instructions. Okay, and the last one is very important to support conditional execution. Okay, think about high level code like if statement. Then you want to do addition operation, otherwise you want to do subtraction operation. Condition check, right? Okay, if condition is met, then CPU supposed to execute addition operation. Otherwise, CPU ignore jump branch, in other words, right? CPU should branch to this place and execute subtraction operation. Okay, and not only if statement, but think about this while statement. As long as this condition is met, you have to keep executing this while loop. Okay, then you exit. Okay, while and case statement and for statement in C. Conditional execution. Okay, condition is met, then you keep executing this. Otherwise, you exit, you branch, right? Something like this. So for that purpose, you need branch instruction. Okay, branch. So there are 3 categories of instructions you have to study before you write assembly program. Okay, so you have to study those instructions. Other instructions are there for performance reason. Okay, for example, AES instruction, AES. So encryption instruction, AES encryption for security, right? You want to encrypt some data. Okay, encrypt data with that AES instruction, and that instruction is there for performance reason. If you don't have AES, probably you can write some software function to do that AES encryption, right? So, but with AES encryption instruction, you can do data encryption, super fast. Okay, super fast. So other instructions again are there for performance reason. All right. Does it make sense? Any question about this? So in this class, we are going to study each category of instructions, ARM instructions. Some background information. Okay, so to refresh your memory. So Intel case, x86 case, right? So levels of program, high level code, and using GCC, then you can compile it. Then you can do object dump, disassemble that binary to see what kind of instructions compiler used to implement the C program. So that is one example, right? So that statement A is equal to 3 that got translated to move instruction. Move instruction is essentially in Intel x86 memory read instruction. You want to read from this memory location, then place into sorry, this is not the memory write. This was memory write. Storing 3 to that place, storing 9 to that place. Okay, so here you are reading. Look at this same location, C, right? C, EBP, same location. Placing that guy into register, placing that guy from this memory location to EDX. Then you are asking addition operation, okay? Because C, addition operation. Some x86 instruction. Okay, we are not that interested in x86 because we are focusing on ARM, but it is not that hard to interpret that instructions. Okay, so memory write 3 to that location, 9 to that location, then read from that location and place into EDX register. Okay, read from this memory location to EAX register, then do addition, then memory update. So here, those are called instructions. Then that is the machine code corresponding to the green, right? Green is machine code corresponding to that instruction. So one-to-one mapping, right? Intel defines instruction format. Okay, instruction format, move L instruction. What is the format? It is 1, 2, 3, 4, 5, 6, 7. It is taking 7 bytes. Okay, 7 byte instruction. Addition instruction, that is a 2 byte instruction. It is CISC instruction, complex instruction set. The one characteristic of CISC, instruction length is variable. Okay, some instructions taking 7 byte, some instruction 2 byte, some instruction 1 byte, and so on. But the RISC, all the instructions are the same size. In ARM CPU, ARM instruction, 32-bit. Right? ARM instruction, 32-bit in size. Okay. Okay, that is one. So in ARM case, okay, in ARM case, you write this code, then using GCC to compile it, then you will get this kind of instructions. Okay, so if I interpret this SLL, because we are going to study those instructions. The first one is a shift instruction. You want to shift, okay, R5 register by 2-bit. So second instruction is very obvious, right? Addition. Okay, very intuitive, right? R4 register, reading R4 register, then reading R2 register, these two, reading this one and this one, do addition operation, then write to which one here, R2 here, okay, R2. And third and fourth, memory read instruction, LDR, right? LDR, memory read from that location to R12 register. Okay, reading from this location, R10. Then next to two, STR, memory write instruction. Okay, memory write. Okay, R10 register to the location. Then the last one, branch. Okay, branch to there is no label, exit, right? Exit, some label. And this one is object or binary code, one-to-one relationship, right? Shift instruction, for example, is corresponding to that 32-bit binary. Okay, and addition instruction is corresponding to this, and so on. Okay, one-to-one. Okay. In this class, we are not going to talk in detail about instruction encoding, that instruction encoding. Okay, because it is the ARM. It is a little bit complex. Okay, and we are not going to design CPU. Okay, ARM CPU. We are going to write, program software. So we are not going to study in depth about that instruction encoding. Okay. Okay. Still some background. This one. Chaeyeon, can you please?
Complex instruction set computer. One assembly instruction does many complex jobs. Variable length instruction. Example x86, Motorola 6080. RISC reduced instruction set computer. Each assembly instruction does a small unit job. Fixed length instruction. Load store architecture. Example MIPS ARM.
Okay. I guess. Chaeyeon, did you take my architecture class before?
Yes, last semester.
Okay. CISC and RISC. Probably I don't want to spend too much time on this. ARM is implementing RISC instructions, and x86 is implementing CISC instruction, right? What is the difference between two? Conceptually, it is very simple. CISC stands for complex instruction set, meaning that complex instruction, each instruction is doing very complicated, very complex job. Okay, and move S is good example in Intel x86, right? You want to move S is what? Move string, right? Move string. Move string. One example is HELLO. You want to HELLO. Okay. You want to copy this string from this source location to destination. Okay. With you can copy H to here, E to here, L like this with one instruction. Okay. It is actually very complicated operation from CPU standpoint, because you have to copy that guy H first, then store, then increment address, source address, okay, to read next character and store to here, then repeat this 4 or 5 times, 1, 2, 3, 4, 5, right, and stop. So this whole operation is done by just one instruction. It is very complicated operation from CPU standpoint, right? So move S, but whereas RISC reduced instruction set, right? Each instruction is doing very small job, unit job. Okay. So to copy that string to this destination location, RISC CPU, you have to use many different instructions. First, LDR, memory read instruction. LDR actually byte, LDRB, to read first byte, first character. Then store to destination using store str byte. I want to store byte. Then increment that address, okay, to point next location with addition operation. Okay. Then you repeat this one. You have to implement for loop. Okay. So each instruction is doing very small job, right? Memory read and memory store and addition, right? By combining those instructions, you can do string copy. Okay. So those are that is good example. And one characteristic of CISC is a variable length instruction. x86, and I showed you that example code, right? Variable length instructions. This one, 7-byte instruction, 2-byte instruction, 3-byte instruction. Instruction length is variable depending on instructions, right? Instruction size is different. Whereas RISC instruction set, instruction size is fixed. In ARM case, 32-bit in size. Okay, let's move on. Okay, the real stuff now. Okay, this one, Day, can you please? Day? Kim Dae-hee? Oh, okay, you are in the library. Okay, thanks. Sang-won? Kim Sang-won?
ARM is RISC-reduced instruction set computer. x86 ISA is based on CISC complex instruction set computer, even though x86 internally implements RISC like microcode and pipelining. Suitable for embedded systems, Cortex-M, very small die size, low price, low power consumption, long battery life.
Okay, thanks. ARM instructions were created with RISC philosophy in mind. Okay, ARM instruction set architect had RISC philosophy in mind and created many different instructions. Okay, so x86 is a good example of CISC instructions, CISC computer. But x86 internally implement RISC-like microcode and pipelining. What does that mean? So if you have studied x86, right? x86, I explained move S instruction, okay? Move string instruction, and that instruction is called actually x86 instructions, right? People call this macro instruction. Macro. They put this word in front of this instruction, macro instruction. Each instruction, right? x86 instruction is called macro instruction. Why they call it macro instruction? Then there is micro instructions. There are micro instructions. Yes, micro instruction is there. Where? Inside the CPU, x86. So you have move S instruction, and CPU read that instruction for processing, right? Instruction patch. Then internally in x86, there is a memory called microcode ROM. Microcode ROM. So move instruction, okay? To execute move instruction, CPU internally execute bunch of microcode, okay, from this point and that point. And each microcode is the same size. Okay, for example, that is 250 bits. Okay, so to execute again, move S instruction, macro instruction, internally inside the CPU. Inside the CPU, CPU is executing some microcode. Okay, read some microcode and let it flow through pipeline, CPU pipeline, right? Remember instruction patch, decoding, execution, and so on, those pipeline. And reading second instruction, let it flow through this pipeline and so on. So internally, that macro instruction got translated into this micro, same sized So it is like a RISC style instruction, okay? And it goes through this pipeline for execution. So if you are interested in x86, probably you read some articles, then you run into that terminology, like macro instruction and micro instruction, right? So some side story. It is not that important in this class. So x86 internally implement RISC-like microcode. This RISC-like microcode and pipelining. And ARM architecture is suitable for embedded system, especially Cortex-M. Cortex-M, because it's very small. It is using small number of transistors. All right, this is a real stuff now. Okay, this one is important. You have to live with the register throughout this semester. Okay, so important slide. In ARM, there are 16 general purpose registers. Okay, you have ARM CPU, you have R0, okay, R02, R15, okay, registers, okay, only 16 registers, okay, and that is the view of register, okay, and one more important thing is ARM is providing how many? User mode, system, hypervisor, supervisor mode, abort, undefined monitor, interrupt. IRQ is interrupt. FIQ means fast interrupt. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 different operating mode. Okay. 9 different operating mode. In user mode, you can see R0 to R15, those registers. R0 to R0 to R12. SP means stack pointer. So R13. Okay, so let me show you. So R13 is a stack pointer. Do I have here? R13, stack pointer, R14, link register. Okay, let me explain some more. Okay, then R15. So again, SP. SP is R13. LR, link register, is R14. And PC, program counter, that is R15. Okay, here. So different name of R13, stack pointer, okay, link register, program counter. The program counter, okay, program counter is what? Pointing the location where you want to read the instruction from. For example, here you have addition instruction, okay, LW. You want to read that instruction. If program counter is pointing that location, PC, right? Program counter, right? And this empty boxes, okay, empty boxes. Empty these boxes, this one, empty rectangles, okay? That means they are using the same register, same physical register. For example, IRQ operating mode, you can see the same R0. You have only R0 to R7. R7 to R8 registers, these 8. So regardless this operating mode, you are using these same physical registers. So I don't care about this operating mode, right? You see the same register, R0. That R0 is R0 still, system mode. Supervisor mode, you are still looking at this one, R0. IRQ mode still R0, same, R0. But here, R8, okay, here FIQ mode, fast interrupt mode. Same R0 to R7, but physically different R8 to R12. So 1, 2, 3, 4, 5. Those 5 registers are physically present. Okay, physically separate register. Only for FIQ mode. Okay, and then R13, R14, R13, R14. You have dedicated registers for each operating mode. Supervisor mode, you have your own R13, R14. Abort mode, you have your own physically different R13, R14. IRQ mode, physically different R13, 14. FIQ, physically different, physically separated and different R13, 14. So how many registers are present? Then you can count, right? How many different registers? 16, R02, R13, 16, 17, 18, 19, 20, 21, 22, 20. You can count. Okay, those are physically present registers. But each operating mode, right? Each operating mode, you are able to see only these 16 registers. Okay, so if you turn on that board, so if you turn on that system, then the ARM CPU goes to supervisor mode. It starts from the supervisor mode. Okay, as the name implies, you have all the power, all the privilege to touch everything. Okay, and user mode, you are just a user. You are limited to do some operation. You cannot touch some very important system registers, for example. Okay, now, those are general purpose registers, right? This one GP registers, and inside the CPU, not only GP registers, but you have many different system registers. So before normal operation, before user operation, you have to set some configuration. You have to do some initialization with those system registers. The thing is, in user mode, you cannot touch those system registers. It is a job of administrator. Think about the Linux system, Linux computer system. You have some supervisor, administrator, and simple user, right? You are creating some account. You are asking some account from administrator, right? Then you can do some limited jobs like application programming, right? You cannot touch in Linux system. You cannot touch IO devices directly with your program, right? Those can be touched. Some registers in IO devices can be touched by only system administrator, right? Supervisor, right? So that is called privileged mode. In user mode, you are less privileged mode, and system mode, hypervisor, all 8, you are in some privileged mode. So in privileged mode, you can touch everything, almost everything, right? Anything you want. So privilege is implemented not only ARM CPU, but privilege, PRIVILETGE, right? Privilege is provided not only ARM, but x86 and RISC-V. you name it, right? Every CPU is providing some kind of privilege, right? In x86, privilege is called ring 0, ring 0, ring 1, ring 2, ring 3. Okay. And RISC-V, in computer architecture class, we haven't talked about privilege, right? In computer architecture, but RISC-V is also providing privilege, right? Like user mode and machine mode, and in between supervisor mode, supervisor mode. So that is most high privileged and less privileged, your user, right? So every CPU is providing, privilege, some kind of privilege mechanism. You reset, you start your computer, you goes into the most high privileged state. You can do anything you want. You have all the power when you turn on the computer. Okay, and with that, with that power, you can initialize the system and switch it to user mode to run some application program. Okay, does it make sense? Okay, registers. Okay. Okay, this one, some terminology. Okay, some terminology. This one, 찬우, 조찬우. Okay, Juan, can you please? Juan, where are you? Probably I have to ask every one of you to turn on the video because I don't know what you're doing, right? Behind the camera. Okay. Okay. So how do you pronounce your name? Abu Salomov?
Yeah,
Absalomov.
you're right.
Okay, can you please read?
Unbanked registers R0 to R7. Each of them refers to the same 32-bit physical register in all processor modes. They are completely general purpose registers with no spatial uses implied by the architecture. Banked register R8, R14, R8 and R12 have no dedicated special purposes. FIQ mode has dedicated registers for fast interrupt processing. R13 and R14 are dedicated for special purposes for each mode.
Okay, thanks. So R0 to R7, those 8 registers are called unbanked register because regardless of this operating mode, you are using same registers, same R0 and R7, R0 to R7, unbanked. And R8 to R14 are called banked register. For example, here, FIQ mode, you have your own R8 R12 and R13, R14. Okay, and FIQ mode, you have your own stack pointer and link register. Monitor mode, you have your own R13, R14 stack pointer link register. That is why those registers are called banked. Okay, banked register, depending on operating mode, system mode, supervisor, undefined, depending operating mode, you are looking at physically different registers. Still R13, R14, right? Still R13, R14, but you are accessing physically different registers. Okay. Okay, so this one FIQ mode, you have dedicated register for fast interrupt. We will talk about that later on. Okay, when we talk about interrupt. Okay, interrupt. Not today. Okay. So banked register, and unbanked registers. Okay. Okay, this one. This one. 찬영, 이찬영.
Do you hear me?
Mhm.
Some registers in ARM are used for special purposes. R15 equals PC program counter. X86 uses a terminology called IP instruction pointer. And R14 equal LR link register. And R13 equals SP stack pointer.
Okay, thanks. Let me explain some important registers. Okay, those three, R13 to R15. R15 is a program counter. Okay. In RISC-V, remember? In RISC-V, you have how many registers? X02, X31, 32 general purpose registers, and you have separate program counter PC in RISC-V, right? And that program counter is pointing the location, memory location, where you want to read instruction from. Okay, that instruction. Okay, you are reading that instruction. Okay, so same program counter. Okay, in ARM CPU, PC is part of general purpose register. Okay, part of R02, R15. Okay, same program counter. And R13, different name is stack pointer. Okay, stack is used all the time to run your program inside the CPU. That is why one register in GP registers, one register in register file is used only for that purpose, stack operation. So in ARM CPU, R13 is stack pointer. Remember, RISC-V, what is stack pointer? Which register? You got brainwashed, right? You don't remember anything after vacation, right? I know, right? So X2 is stack pointer. X2 in RISC-V. Intel x86. x86 has also stack pointer register. x86. X86. The 32-bit x86 has only eight general purpose registers. Only 8. EAX, EBX, ECX, EDX, and one is ESP, stack pointer. So one register in this precious register file, only 8, right? Only 8. One is used for stack operation, stack pointer. Okay. So the point, every CPU is providing one register for stack operation, stack pointer, right? Stack pointer. So R13 is stack pointer. And our link register, right? Link register is used to do what? Used to store return location. When you make a function call. Remember, you are making a function call. You are calling main, right? From main, you are calling foo, right? Foo function, foo. Okay. So after running this foo, executing foo function, you have to return back, right? To return back, you have to store this return location, this location one. Okay, that is the location you have to return. Okay, and that location is stored in this LR register. Remember in RISC-V, which one is link register? Remember X1, right? X1, different name is link register, X1, right? So, you know, many things are common. Many things are common in, many things are common regardless of, you know, different CPU, x86, the RISC-V, ARM, MIPS, many things are, you know, common, many things, right? So if you understand one CPU, RISC-V, and very easy to understand, you know, ARM, right? They have stack pointer, link register, stack pointer, link register. You know why you need stack pointer, why you need link register, why you need program counter, right? You know, right? That is why you can, you read datasheet, ARM architecture reference manual yourself, then you can understand. Once you understand, you know, one CPU, you know, completely. Any question about this? So, you know, many aspects are common. That is good news, right? You study one CPU, then super easy to understand other CPUs. Right? Okay, this one. Okay, this one. Nadira.
Cpsr. Current program status register Cpsr is accessible in all modes, contains all condition flags, interrupt disable bits, the current processor mode. Do I have to read all
No,
the table?
thanks. That is enough. Thanks. Thanks very much. Okay, Cpsr. This one super important register. Everything is very important. Cpsr, current program status register. Okay, Cpsr register. So in addition, in ARM CPU, in addition to this general purpose registers, register file, right? GP registers, you have separate register called CPSR, current program status register. Okay, and that is the shape of CPSR register. 32-bit status register. Here you can by looking at this, you know, for example, M means 5-bit, right? 0 to 4. So 5-bit. Next slide. Look at this encoding. Operating mode, right? User mode, FIQ, 9 different operating mode in ARM, right? And user mode, the M field contains 1 4 zeros. Then you are in user mode. Okay, 28. Okay, here M. Here you have 1 4 zeros. Then you are in user mode. Okay. Then, for example, you have 1 2 zeros, 1 0 0 1 1. Okay, 1 0 0 1 1. Then here 1 0 0 1 1. Then you are in supervisor mode. So by looking at this M, you know, field, you know which mode you are in. You are in user mode, supervisor mode, you know, FIQ mode, IRQ mode. By looking at this, you know, right? And also, so we will talk about, you know, these different fields, right? Different field T, F, I, you know, as we move on. And one important field is NGCV. Okay, NGCV. I know you don't remember anything, right, from architecture course. So NGCV. Okay, so read this, NGCV. N flag, right? N flag. Those 4 flags are used to NGCV. Those 4 flags, each one is 1 bit. Those 4 flags can be used to compare integer, right? So the example is, so C, right? So A is equal to B. Then you do C++. Otherwise, C minus minus. Okay. So you want to check equality, right? And how to check the equality, right? In ARM CPU, you have to use compare CMP instruction, compare instruction. Okay. Compare. Assume that A is contained in R2 register, B R3 register. You compare R2 and R3. You write this instruction. You use that instruction. So then compare, right? Compare is what? Compare is inside the CPU. It is doing subtraction. R2 minus R3. Compare, right? Then based on that outcome, CPU is going to set those flag registers. Okay. So in this case, if assume that this one contains 5, and that is also 5. 5 minus 5, right? And 0. In this case, 0 flag will be set to 1. 0 flag. We will talk in detail because it's so important, very important feature. Okay. In ARM CPU, not only ARM CPU, but very important mechanism. So we will talk in detail about this. So the point is, using these 4 flags, you can compare those integers. Okay, integers. Not only this equality, but you want to do equality or greater than or less than or that comparison or that comparison. Okay. So 1, 2, 3, 4, 5 different. Also one more thing, right? Not equal. Okay. 6 different condition with your program, right? Sometimes you want to check this one, not equal. Okay. And also one more thing is, AB, is it signed integer or unsigned integer, right? So depending on your data type, if you use int data type A and B, then A, B are signed integers. If you use unsigned data type in C, unsigned AB and AB are unsigned number, 0 or positive. Unsigned, right? Unsigned integer. So you can do comparison of signed integers and also unsigned integer by looking at this, by looking at these 4 flags. That is, very amazing, right? You use the same compare instruction, and compare instruction will set those flags. And by looking at these only 4 flags, you can tell A is not equal to B, or A is greater than or equal to B, or less than, okay, for integer or unsigned integer. That is the one, okay, NGCV. N means negative flag. Negative, what is negative? How do you know? In computer is using 2's complement, 이해 보수, right? 2's complement here. 2's complement, right? 2's complement number system. So if MSB, okay, MSB, ALU is doing computation and most significant bit, 32-bit, right? 32-bit output, and MSB is 1, most significant bit is 1, then you think of it as a negative number. MSB is 1, then you think of it as negative number if that is signed integers. If you are doing some arithmetic operation for unsigned integers, then MSB is 1, then that is not negative number, still positive number, right? So I think you remember my lecture last time. It depends on your interpretation, right? Data interpretation. CPU will give you same data, but the output is positive integer or negative integer. It depends on your interpretation. Okay, if you think of it as signed integer, then negative number, MSB is 1. Okay, if you think of it as unsigned integer, then you're not negative. That is positive, right? Big number, some big positive number. So N, right? N flag, zero flag. Zero flag is easy, right? Zero flag. And carry flag, carry out, right? Carry out. Only carry out flag. And V means overflow flag. Okay, we'll talk in detail. Okay. So the thing is, so this one is from the ARM technical reference manual. Let's okay, so C flag is used to check C flag is used to compare unsigned, right? Unsigned numbers. And V flag is used to compare where is that? Signed, right? Signed numbers. Okay. Again, C is used to compare unsigned number. You think of it as unsigned numbers. R2, R3 contains unsigned numbers. Then you need to check C flag. You consider those numbers as signed numbers. Then you have to check out V flag. V flag. Okay, we will talk about it. For now, think about that. And actually, I don't want to explain in detail why you have to look at C, why you have to look at V. If you are curious, because that will take 1 whole hour to explain, right? So if you are curious, you check out this one, digital logic design. Okay, ID COSE 221, same password, right? COSE 221. Then go down, check out this subtractor, adder and subtractor. So here, overflow. It is talking about overflow, right? ALU is doing addition operation, and there is a limitation, some range of numbers you can represent with a 32-bit. What if the output, addition output, is bigger than the largest number it can represent? Overflow, right? And underflow, you do subtraction, right? Then that goes beyond the the smallest integer it can represent. Okay. Okay. So using overflow and underflow, you can you set carry flag, so unsigned number subtraction, and signed number. Okay, signed number subtraction, then overflow and underflow. So things. Okay. So here NGCV stuff. Then can you? So you want to check out this condition. If UA is bigger than UB, then you have to check out carry flag, unsigned higher. So I don't want to go through, this slide because again, it takes, 1 whole hour. Okay, same, same table, right? So check out this PowerPoint. On sign number. Okay. And we are still talking about Cpsr, right? Cpsr, you have A bit, I bit, F bit. Let me go back to page 28. Here, A bit, I bit, F bit. With I bit, if you set I bit, that means, okay, I don't want to take interrupt. Interrupt is masked. Okay, that is the one. Let me go to here. Oh, sorry. I bit, you are disabling interrupt if it is set. Okay, so that means what? CPU has at least one input to take interrupt. Physical wire to take interrupt from I/O devices like keyboard, okay, and mouse. And so this one also, this spotlight, if I press this, okay, like this, then interrupt is generated inside the computer. So that is why. So how does my computer know if I press this button or not? CPU is taking interrupt if I press it. If some event happens, through that connection, if I press it, through that connection, some event happens. This line goes up like this, 0 to 1, okay, time. When I press the button, okay, then CPU, okay, recognize, okay, some event happens. Then what do I have to do? Then it follows the protocol. Okay, event happens, then okay, I'm supposed to do something. We'll talk about that later on. Okay, so but if you set I bit, okay, I bit to 1, then okay, CPU said, okay, I'm not, even though you press the button, I'm not going to take that interrupt. I'm going to ignore whatever you do. Okay, I'm going to ignore your request. I'm busy. I have to do something. Okay, I'm going to ignore. F bit, set this bit to 1, then you are not taking, you disable. Okay, fast interrupt is disabled. Okay, and so on. So that is some exception. So interrupt and exception. We'll talk about those things in detail when we discuss interrupt and exception. For now, don't worry too much about this. Okay, we are going to come back. And so still, status register, Cpsr register, JBit and TBit. So JBit, if you set JBit, TBit to 00, then you are CPU are ready to execute ARM instructions. Okay, JBit. What is JBit? J and T. JBit. Okay. You can think of it as Jogel bit. Jogel, right? Last time we talked about bytecode, Java bytecode, right? Jogel, right? JBit and TBit, sum. Okay. Cortex is providing Cortex can execute. Cortex A can execute 3 kinds of instruction set. ARM instructions, and sum 2 instructions, sum 2, 16-bit, 32-bit, both. Okay. ARM instructions, sum instructions, and Jogel bytecode instructions, right? Bytecode or instructions. 3 different instruction sets, Cortex A. So you can select, okay, now I want to execute ARM instructions in Cortex A. Okay, I want to execute some instructions in Cortex A or Java bytecode. Okay, then you have to change that bit J and T bit like this. JT00, then CPU is ready to execute, ready to take ARM instructions and execute. Okay, and 0, 1, sum is 1, then CPU is ready to execute sum2 instructions. Read sum2 instructions from memory and execute it. Okay, 1, 0, 저zel instructions, Java bytecode. 1, 0, then CPU is ready to execute Java bytecode stored in memory. Read Java bytecode and execute it, right? Okay, and 1, 1, that is, according to the specification, that is deprecated. It is no longer used. So you can ignore some EE. Okay, ignore that part. Only these three. Okay. Okay, one more thing. Okay, Cpsr. Here, different name of Cpsr is APSR. Application current program. Application, what is it? Program, right? Application program status register. Same physical. It is talking about same physical register. But why use different name? Why use different name? For readability. What do you mean by that? In Cpsr, if you use Cpsr, okay. So APSR format, compare that with Cpsr. Same physical register, NGCB, NGCBQ, but some fields are not accessible, or some fields are not programmable in, if you use APSR. So the thing is, look at this, mbit, using mbit field, you can change operating mode. That is very dangerous operation. You are in user mode, you are not supposed to touch, mbit. Okay, you are not supposed to touch ibit, interrupt, enable, fast interrupt, enable, and T, J, that operating mode, right? That is very critical operation. So you are in user state, user mode. Okay, don't touch it. Okay, because that is very dangerous. You are in supervisor mode. You have all the power. Then you can touch. You can touch J and T, those bits. Okay, so you go to supervisor mode. Then you can use those Cpsr. In your program, you can use Cpsr name. But if you are in user mode, instead of using Cpsr, then use APSR. Okay. Then other people look at your code. Then you write, you have APSR code in your program. Then other people know, okay, you are in user mode. So for readability, okay, for not confuse other people, okay. But it's okay to use a Cpsr. But you can use Cpsr in your program, but still you have a limitation. You cannot touch. You cannot touch, those important, bits. Okay, one more important thing before letting you go. Status register. Status register is present not only ARM CPU, but every CPU. Intel x86, right? So many things are common, right? So x86, what is status register in x86? E flag registers. E flags, that is the status register. Similar function. Okay. RISC-V, we haven't talked about status register in architecture class, but RISC-V has also, the register for similar operation, similar function, M status register in RISC-V, x86 E flag register, ARM Cpsr register. So many things are common. Okay, so that is good news, right? It is not only for the Cpsr status register is not only for ARM. Every CPU has status registers. All right. I think this is good place to stop. Okay, so we are going to skip interrupt. Okay, later on we will talk in detail about interrupt. At the time we will revisit this, PowerPoint. Any question before closing up? Okay, from next time, we are going to play with this Eclipse environment, right? I ask you to set up that tool, right? Vivado. Okay, we are going to use that the environment to write program and show you demo. Okay, so that is example, right? So after setting up everything, you are supposed to do this one here. Play with, write some code. For example, addition R2, R3, R4. Okay, then compile it. This compile, build. Okay, and check out some machine code if you are interested. And here, search with main. So the code I just wrote got got generated addition instruction, then machine code, right? And memory location, right? So you can play with ARM instructions. Okay. Okay, I guess that's it for today, and I'll see you next time. Okay, bye. Yep, thanks. Thanks.